All right, in this next section, we're going to be getting into specific types of sequences now, which I kind of mentioned when we were in that first section, because we went over how there could be like a arithmetic sequence or a geometric sequence. So this section is going to just focus on arithmetic sequences, how to maybe find the next couple of terms in a sequence, but then also how we would write an arithmetic sequence, how we would write the formula that would represent the situation that's happening. And then in the next section, we'll talk about geometric sequences, which was the other one. Now, if you remember for arithmetic sequences, I said these are created by either adding or subtracting the same number over and over and over again. And a geometric is when you're multiplying or dividing, okay? So we're going to talk today about how you find the common difference, how you write out the terms of a sequence, and how you can create a formula and then use the formula to either find more terms or find a specified term that they want within the sequence. So remember, an arithmetic sequence, like I said, is the difference between the terms would be the same. So you're adding the same amount or you're subtracting the same amount. So it's increasing or decreasing by a common number. First thing we need to do is, like, if they gave me a sequence and they wanted me to understand if it was arithmetic or not, like figure that out, I would need to know what's the common difference. How much is it increasing and decreasing between terms? So for example, if I had 5, 7, 9, and 11 given to me, and they wanted me to figure out if it was arithmetic or not, I would need to know what's the common difference. The best way to do that is to either just think about subtracting, like the second term minus the first term, and then the third term minus the second, and we keep going up in that pattern. Or if you can work with it mentally, you could just think, what are they adding by each time? Some of you might be able to see each time it goes up by 2 between each term. So that would be another way to tell if it's arithmetic or not. They're just showing you with a common difference. 7 minus 5 is 2, 9 minus 7 is 2, 11 minus 9 is 2. So since I'm getting 2's all over the time, that means it's going to have to be arithmetic. If I'm not getting the same difference between them, then it's not going to be arithmetic. It could be a different type of sequence that we're not there yet with. So let's do this next one. We've got 1 squared, 2 squared, 3 squared, 4 squared. I would maybe start by actually evaluating that. So 1 squared would be 1. What's 2 squared? 3 squared? And 4 squared? 16. Okay, if we think about what's happening here, what did they do to 16 to get to 9? 16 minus what is 9? 7. 9 minus 4, or 9 minus what is 4? 5. And 4 minus what is a 1? 3. So I'm not getting the same number over and over. These are all different numbers. So this would not be arithmetic. So we would say no, not arithmetic. Has to be the same difference. That one does not come out to be the same number repeatedly, so it's a no. Okay, so once you can figure out the fact that they have to be increasing or decreasing by the same amount, then they may start giving you a formula that we use to represent what's happening in our sequence. And then they might give us the first term of the sequence and then want us to find more. So this next example wants me to write the first 5 terms of the arithmetic sequence here. They're telling me that the first term is 100. That's what that a sub 1 means again. That's your first term. Underneath it here, they're giving us the actual rule for this sequence. So it says a sub n. That would be for any term or any number of terms that I wanted to maybe find. What I'm going to do is take a with n minus 1, so the previous term that we found. That's going to be kind of like using the recursive formula that we talked about in that first section. And then it looks like they're subtracting 30. So the first term they gave me was 100. So this 100 comes down into that a sub n term. So it just got dropped into this piece here. And then you subtracted 100 or 30. So 100 minus 30 gives me 70. And then that would be the first, like, next term. They want me to find the first 5. The first one's 100. The next one would be 70. Then I would take 70 in and subtract 30. That's how I get 40. The next one then would be 40 minus 30, which is how much? 10. And then the next one would be 10 minus 30, which is negative 20. So the first 5 terms would be 100, 70, 40, 10, and the negative 20. And then I could keep going if they wanted me to, but they just wanted the first 5 terms, so you can stop right there. Okay, why don't you guys try that next one? They're giving you a new first term and a new arithmetic sequence. So go ahead and see if you can find the first 4 terms of this next one. All right, so your first term should have just been the 24. And then you're adding 5 each time. So what's the next one?
29.
The next one?
34.
And the next one?
39.
Very good, thank you. So those are the first 4 terms of your sequence. And again, we could keep going if they wanted me to. All right, do we have questions on how to use an arithmetic sequence like that? Okay, if you guys turn the next page, what I want to go over next then is how you would actually write an equation or write out an arithmetic sequence if you know some information. Now, in order to do this, you need to know a couple of things. You would need to know the first term, like you would need to know a term from the sequence. You would need to know where that term is at. So where along in the sequence are we at? Are we working with the 3rd term or the 15th term? We would also need to know the difference between the 2 terms. Another way to think about this, because if we think about arithmetic sequences on a graph, they're linear. So it'd be like thinking about what's the slope, what's the common difference between the numbers. I need to know some of those things in order for me to even be able to write an arithmetic sequence. Now the formula looks like this here. And it has a lot of these pieces with letters in it. When you start to do an example, you'll have some of these pieces given to you and you'll start plugging them in and working with it. The a sub n is going to be just like the generic form of any term that you're trying to find. So we may not ever plug anything in for a sub n unless we're actually looking for a term after we write out our sequence. A1 though would have to be given to us. I need to know like what's the first term of my sequence. I would need to know the position of the term if they wanted me to find one in the future. And then I would need to know the difference. So for most problems, when you're writing an equation, you may not be given the an or the n. That might be used later if you're actually trying to evaluate the sequence at something. So let's go over an example of how we would write out an equation. If I'm given this series, 14, 17, 20, and 23, this would be like my sequence here. I can look at that and grab a couple things. The 14 would be my first term. This would be the A1. Okay, and so I would use that in my formula. The other thing I need to know, though, is the difference. Like, what's the common number that it seems to be doing here? And I always think about the difference, like going down. So 23 to 20, 20 to 17, 17 to 14. What does it appear it's doing every single time? Going down 3. So I would say my difference is 3. Okay, so that's what they have written here. My D difference is 3. So using the general form of our equation, I'll just write that again here. The general form says A sub n equals A1, your first term, plus the difference times n minus 1. And they're starting to plug these pieces in. Notice how they don't plug anything in for an. I told you that we probably won't do that. But the first term, A1, we said from our sequence was 14. So 14 goes in for the A1. 3 is our common difference. So that goes in for our D. And then again, we're not plugging anything in for the N. Once you get it plugged in, then what you're going to want to do is simplify. So I distribute the 3 here. into the parentheses. So now it says 14 plus 3n minus 3. And then I can combine the 14 and the 3 because those are both just numbers. So this would become 3n plus 11. This would be the equation that I could use to represent the series that I was working with, but also use it to help me find the next term. And they are showing you how to do that on the next kind of step underneath it here. Underneath it says, find the 56th term. To do that, you just plug 56 in for n. And you could go either here or you could go here to do that. Most of the time, I'm going to use the simplified version, so I would probably resort to this one if I was given a choice. So I would take 3 times 56, add 11, and you would get 179. So that would be the 56th term in the sequence. And then I just talked about this a little bit ago, but this is showing you that arithmetic sequences are linear. They form a straight line because you're just going up the same amount. So it would have a constant slope. It would have a constant increase or decrease. All right, so why don't you guys read through the next one and see what you can do. Try to write out a formula. This is your kind of framework to be working with here. Read the problem, find what your A1 is and your difference is. Try to write out an equation and then see if they want you to find a future term. All right, what'd you guys put in for the A1? Good, 6. What'd you put in for the common difference? Good, -5. And then this is still times n minus 1. Okay, I would have distributed the -5. So you just want to watch your signs here. So we have 6, and then this would become a minus 5n, and then a plus 5. So if you wrote out your general form, what did it say? Good. -5n plus 11. There's my equation. So that was the first thing that I think the problem asked for, is to write the arithmetic sequence. So there it is. And now I want to find the 9th term. How do I do that? Yeah, plug 9 in for n. So take -5 times 9 plus 11, and you get -34. So I would write it like this. A with a little 9, because we're talking about the 9th term, would be -34. Okay, any questions on writing a formula like that? Okay, now that's kind of just if they're just giving us numbers. If you guys go to the next page, we're still doing the same idea, but they're just putting some context into the problems now. So this first one says data on this graph showed that in 2010, 16% of the U.S. population was Latino. On average, this is projected to increase by approximately 0.35% per year. Write a formula for the nth term of the arithmetic sequence that describes the percentage of the U.S. population that will be Latino n years after 2009. Okay, and we could do this for anything. We could have picked any of these groups over here from the graph and done this too to see what the population would be for any of those as well. So they chose this one. They're saying that the first term is 16, and that's coming from the 16% from the information given above. It's also shown here on the graph. So your first term is 16. They're saying that it's increasing by 0.35% every year. That's your difference. So that would go in for your D. So they just plugged it into our general form like we were just doing. They simplified by distributing that 0.35 in. and then combining any like terms, and they end up with this as their equation. So it's no different than what we were just doing. And then they said, all right, now that you have an equation, what percent of this population is going to be Latino in the year 2030? Remember, the equation that we have, the sequence that we have, is starting from the year 2009. So they had to find the difference first to figure out what term are we even looking at here. So 2030 minus 2009 is 21. So that's going to be the term that we're looking for. So then you plugged in 21 for N, you solved it, and it gave us 23. So that means 23% of the population. Okay, so on this next one, similar idea. They're just giving us another example of context here. So it goes on to say, data shows in 2010 that dormitory charges were $5,249 at private schools. On average, the cost increases $198 every year. Write a formula of the arithmetic sequence, and then what will it cost in 2020? So what's my first term? What's the difference? Good, 198. So let's plug this in. So it'd be 5,249 plus 198 times n minus 1. We would start first by distributing. And you should be able to combine just the numbers here. So it's 198n, and then what? Plus, good, 5051. Okay, so here's our equation that we're going to use. Now it goes on to say, what will it cost in the year 2020? So the year that this started was 2010. How many years have passed? 10. So we want to put it at 10 for our n. So 198 times 10 plus 5,051. How much will this cost me?
$7,030.
And again, I would write that like A sub 10 because it's the 10th term, since it's been 10 years since this sequence started. All right, any questions on that so far? Okay, if you guys turn the page. All right, so like we saw yesterday with the end of 8.2, we talked about the summation notation, which is when you evaluate a sequence over and over and over again, and then you want to add up all of those terms that you had. We can still do that for an arithmetic sequence. So the S that you'll see here with the little n, that's just the notation to represent an arithmetic series. N is going to just represent the number of terms that we're using. So for example, if I had the sequence 1, 2, 3, 4, 5, the series of the sum of those first 5 terms, so they would write that S, capital S with a little 5, because there's only 5 terms here, you would add up 1 plus 2 plus 3 plus 4 plus 5, and you would get 15. Okay? Now we can find the sum of a finite arithmetic series. And we would maybe want to do this if it gets to be too long to add by hand. Okay? If you remember, like 2 chapters ago now, we talked about that Gauss-Jordan. Okay, so Gauss kind of had a lot to do with like our matrices and whatever. Well, he also has a formula, Gauss's formula. He actually discovered this at age 10. Okay, and how he did this was he was in school, and his teacher, like they were, I don't know, the kids in the room were being a little bit unruly, it sounds like. And so she gave them an assignment that they needed to add up the numbers 1 through 100 by hand. Well, Gauss was being a little bit creative with what he was doing, and he discovered a pattern that if you add like the first and the last number, like 1 and 99, it makes 100 really easily. And so then he did 2 and 98 to make another 100, and he kept doing that to get the sum of all those numbers together. So he actually got it done very quickly, to his teacher's surprise. And so after that kind of happened, he kind of then, proceeded with his math career and whatever. But this was a formula that he then created on his own because he discovered it when he was young, that if you add the first term and the last term of a finite sequence and you keep kind of pairing them up together, it's going to maybe make that sum become a lot easier. So what he is showing on here is kind of just an example of that first 5 series that I gave as an example up above, where it's 1, 2, 3, 4, 5. If I reverse the order of my sequence, so 5, 4, 3, 2, 1, and I add them together, I get a whole bunch of 6s here. Just like when he was adding the numbers 1 through 100, he got a whole bunch of 100s, okay, to start adding together. So when we are doing something like that, there's a shortcut that we can take. We can think about reversing the order. Okay, so if we add kind of our terms here, we're adding those 2 sequences together. We now have 2 times the sequence of 5, and they all came out to be a lot of these 6s, like I said. You could then simplify this because there's 5 of them here. Instead of adding them 5 times, we could just take 5 times 6. And then because there's a 2 sitting out front here, we have to account for that. So you just cut that in half. So when Gauss did this, he was looking at 1 and 99 to get 100, 2 and 98 to get 100. He figured out how many pairs there would be. So there was a whole bunch of 100s. He multiplied, or he maybe added those 100s, and then he cut it in half to account for the fact that he did that. And he was able to get that really quickly. So this formula right here, we can use to help us quickly find the sum of any arithmetic series without having to add all the terms individually. So if I had something like this first example, I wanted to find the sum of the first 50 positive integers, that would be adding 1, 2, 3, 4, 5, all the way up to 50. If I was doing that by hand, it might take me a little bit of time to do that. So instead, what we can do is we can think about our sequence and figure out how many terms there are, how many terms are we looking for, so that's our n. So in this case, if I want the first 50 positive integers, my n would be 50. I take the first term in my sequence, which would be a 1, and my last term in my sequence, which would be a 50. We add them together, and then you end up dividing by 2. So 50 times, this would be a 51, and then divide by 2 gives us a sum of 1,275. So it's a lot faster when you're adding those together. Now, if you think about the next one, it says find the sum of the first 10 odd integers. Okay, so odd is going to change things slightly as far as how we think about this. Think about odd numbers only. What's the first odd number that we have? 1. What would be the 10th odd number? A little more than 11. Because 1, 3, 5, 7, 9, 11, 13. Too big. 15, 17, 19 would be the first 10. So 19 would be your last term in the sequence here. And my total number of terms would be 10. So 1 to 19 would have 10 odd numbers there. So let's plug this into our formula. We're going to do 10 times 1 plus the 19, and then you're going to divide that by 2. So this is going to give me the sum if I was adding 1, 3, 5, 7, 9, if I was adding all those together. So go ahead and do that. What do you get? 100. Good. All right. Are we doing okay, everybody? We've got just a little bit left, so let's keep going, see if we can get this finished here today. Okay, let's do another example of what we were just talking about. So we want to find the sum of this series. Okay, it's 70, 49, and it's going down all the way to negative 749. So again, for this one, if you're going to do this by hand, you'd have to first figure out what's the difference, like what are they doing each time? How did they go from 70 to 49? What did they subtract? And then you have to think about how many other terms are in there. You'd have to find them all and then add them all together. It's tedious. So instead, let's do our shortcut. What's the first term? 70. What's the last term? Negative 749. Okay. I would need to know the number of terms here, which this might take us a little bit more to like think through. It's a little bit harder to think than just like the 10 odd integers. How many terms would be between this? If they're going down, it looks like 70 minus 21. Anyone have an idea how many terms there would be there? No? How would you figure that out if you didn't know? You would use the formula. So if we had, let's see, our formula was n times a1 plus a2 all over 2. That's our formula. But I need to know what that n is. I need to know how many terms there are here. Well, but we don't have anything that it's equal to. I don't know what the sum would be. So we need to find our n. We need to know how many terms there are. So I think what you're going to have to do is maybe just think, how many times do we have to go from 70 to negative 749? How many times do we subtract to get to that? And if you don't know, you're going to have to just probably use a calculator to figure it out. Okay, so I'm going to grab one and do it with you guys. So I would just grab your calculator, start at 70. And we're subtracting, what did I say, 21? And then I would just keep going. I would try to keep track of how many times you're doing this. I got 39. All I did was I started at 70, I subtracted 21, and I just kept subtracting 21. Eventually, it just kept saying answer minus 21, so I just kept hitting my enter button, and I was just counting in my head. So if we plug this all in, it would look like 39 times 70 plus the negative 749, trying to squeeze that in there, all over a 2. This should give me my sum. What is that?
Negative 13,240.5.
Good. There you go. Okay, so well, they got a different answer. So maybe I counted wrong. Oh, I probably didn't count the first one. Okay, so let's see what they did here, because we just did ours by hand. So let's see, I probably just counted this wrong. This should have been a 40, but it looks like they did the same thing that we did. They found the difference, which was a 21, because that's what we saw they were decreasing by each time. 70 was our first term. The last term was at negative 749. And then they kind of worked to find the number of terms. Now, they did use a formula here, but not the same one that we were using. They were actually using the arithmetic sequence formula instead. So they were using that negative 749, like that AN, this one that we just went over a little bit ago. That A1 plus D times n minus 1. So that's what they used here to help us figure out how many terms there were. And so they actually got 40. So I think I just didn't count right. So this should have been a 40 here instead of a 39. And that will probably reflect my answer down here. But so that would be something you could do if you don't know the number of terms, is you can kind of go back a step, use our arithmetic sequence formula to help us figure out how many terms we have, and then be able to find our sum. Once we knew the number of terms, then you can plug that into the formula that we just talked about with the sum. So this one here, and then you can find it. And so that's why ours is off a little bit, because I had counted incorrectly up above. So let's do a practice here. I want to find the sum of the first 15 terms of the arithmetic sequence. So I want to think about kind of, do I have enough information for my formula? The formula that I was using to find the sum is the number of terms times the first term and the last term in the parentheses here, all over a 2. Do we have our first term? Do we have the A1? What's the sequence start at? 3. I don't know where it ends though, right? This is the unknown piece. Now I could maybe find it, okay? What's the common difference? How much does this seem to be increasing, or if you go backwards, how much is it decreasing each time? 3. And I know my n would be 15 because I know that's the number of terms that I want. Now, I don't know what this a sub n is. Again, could I find it? Yeah, I could sit on my calculator and I could add 3 plus 3 plus 3 plus 3 over and over and over again and make sure I do it 15 times. But again, even on that last one, I made a mistake, right? It's really easy to miscount or not count enough where you think you have the right answer. So I would maybe use our first formula. Before we use this one. So I don't know what the last term is that I'm looking for, but I know that the first one I have is a 3. I know my common difference is a 3, and I know that the number of terms I want is 15. If you guys evaluate just that left or the right-hand side, what's the final term going to be? What would be 3 plus 3 times 15 minus 1?
45.
So that's the last term in the sequence. So now we can find our sum, because we already knew that we had the first 15 terms. We said the first one was a 3. We just found the last one to be a 45. And then we can cut that in half. So what's my sum? I have 360. Let me check. Yeah, I got 360. So kind of shows you there how you could do what I tried to do and like add or subtract each time. But there is a faster way to go about that instead of having to just subtract over and over and over again, okay? And it prevents you from making a silly mistake like I did. All right, we've got one last thing to talk about. What we just did there is kind of like what we were using yesterday with that summation notation. We were trying to add up all the terms that we had in our sequence. So we can still do that here on an arithmetic sequence. Remember what we saw yesterday is when you have it written in this sum notation that you've got a lower limit and an upper limit, and you can split it apart if you want to, and then try to like add it all together at the very end. But when you look at this, this actually will help you write it in an arithmetic sequence if you need to. So the lower limit here, 45, that would go in for like the last term that or your first term, I should say. So 45 goes in for the first term. So you're just adding it to find the first one, which is 139. Then you could go on to find the very last term. So 139 would be the first term. Then if you go on and you put the 100 in, so you find the very last term, that's 304. If you have the first and the last term, then you can use that to help you get to your summation. They also are saying, like, what would be the difference here? So to do that, because you know that the lower bound was 45, to find how many terms there are when you're given the lower and the upper bound is you just subtract the numbers. But what I had forgotten to do on that last one when I was subtracting is to add 1 to make up for the very first term. So they're going to take 100 minus 45 here, but then you have to make sure that you add 1 to represent the term that you started on. That's what I had forgotten to do on the previous page. And so 56 is the number of terms that we're working with. So then you can plug it into that sum formula. The number of terms, which is 56, times the first and the last term added together, divided by 2, and you get this 12,404. So let's do this last one here. Let's evaluate for the first term. What number are we plugging in for the first term? 33. So 2 times 33 plus 1 would be,
66.
and then plus 1.
67.
Okay, and then the last term, 50. 2 times 50 plus 1 is 101. Okay, to find the number of terms, we take 50 minus 33 and then add 1. So how many terms are in this sequence? 18. And now we should be able to find the sum. So 18 times the 67 plus 101 divided by 2. What's your sum?
15,003.
15,003? I got 1512. Did anyone else get 1512 or did you get 03? 67 plus 101 is.
Well, I forgot I messed up, so I had 66 down below as well.
Oh, okay. Oh, okay. Times 18 and then divided by 2. Yeah. I see. Okay. All right. That's it for notes there.